Hi guys, welcome back to the channel. In this video we are going to discuss yesterday's problem of the day, and the name of the problem is number of coins. Okay, so you can find the link of the problem in the description of this video, and you can also try today's problem of the day, and the solution for this would be available tomorrow. Okay, so before starting I would like to uh, get a confirmation from you that my screen is visible and I am completely audible. And please write in the chat box if I am completely audible and visible. Okay, and then we will start with yesterday's problem of the day. And as I said, the name of the problem is number of coins. Okay. Hi Chirag, it's clear. Thank you thank you for the confirmation. So this is a very standard problem. Okay, and it's a basic problem of dynamic programming, and it's a the variant of the 01 knapsack. Okay, it's a variant of the 01 knapsack problem. And there are two types of knapsack problems. Okay, the first one is the unbounded and the second one is bounded. Okay, what happens in bounded knapsack is that in bounded knapsack we can pick any element at most k number of times. Okay, or the k value is mostly 1. Okay, so in bounded knapsack we can pick any element. Either we can pick it once or we can just ignore it. But what happens in unbounded knapsack is that, so in unbounded knapsack we can pick any element any number of times we want. Okay, let's say that we have a coin of type 1, so we can pick 3 coins of 1, we can pick 2 coins of 1. Okay, or either we can pick 0 coins of 1. So what happens in unbounded knapsack is that there is no upper limitation of to how many coins that we can pick. Okay, so this is the main difference between the bounded knapsack and unbounded knapsack. And let us quickly read the question, that what is given in the question. Okay, so in this question you are given with a value v and an array of coins. Okay, of size m. So what the size of the coin, size of the array given, that is m, and you are given with a value v. Your task is to make the change for v cents. Okay, so what is your task? You want to make the v change. Okay, you want to make v change. What and given that you have infinite supply of each coins. Okay, so after reading this line, that you have infinite supply of each coin, that is coin 1, coin 2 and coin m. Okay, it means that, let's say that you have coins of type 1, 5 and 7. Okay, you can pick as many ones as you want. Okay, you can pick 3 ones if you want. If you can pick 4 fives if you want. Okay, so that will give you 5 plus 5 5 5. Okay, so it means that this is a type of unbounded knapsack. Okay, so by reading this particular line you should understand that. And what is your task? Your task is to find the minimum number of coins to make the change. Okay, and what is the change that we require to make? That is nothing but this v value that is given in the question. And if we are not able to make the change, then we have to return -1. Okay, so the question should be very much clear. So let's read this first example. Okay, and understand how the output is given. So here the v value is equal to 30. It means that the change that we want to make is equal to 30. Here m value is equal to 3. It means total number of types of coins that we are have. Okay, so we have 3 types of coin. One coin is having 25 value, one coin is having 10 value, and the third coin is having the 5 value. Okay, and we want to make the change 30. So let's see that how we can do that. So our v value is equal to 30. So let me write it here. And we have coins as 25, 10 and 5. Okay, so as we want to make 30, so what we can do, we can just pick 3 tens. Okay, so if I pick 3 10 coins, then it will give me some 30. Okay, or else what I can do, I can just pick 25, one coin of 25 and one coin of 5. Okay, so it will also give me 30. Or what I can do, I can just like pick 4 coins of this, so it will give me 5 plus 5 plus 5 plus 5, so that will give me 20, and I can just pick one 10 coin, okay, from here, so it is also going to give me 30. So there are many possible ways. Okay, what we can do, we can just all pick all 5 coins. Okay, so that will give me 5 plus 5 plus 5. Okay, so this will also give me 30. But what is the question? Okay, the question is, let's see that here we picked 3 coins. Okay, so then we got the sum 20, sum 30. Okay, here we just picked 2 coins. Here we, how many coins did we pick? We picked 4 5 coins and one 10 coin, so total we picked 5 coins. Okay, so here we would have picked 6 coins. Okay, so the question is, you want to find the minimum number of coins that we should pick so that we get this sum that is equal to 30. Okay, and we get this change that is equal to 30. So see here, if you just pick 25 and 5, okay, so you need to only pick 2 coins, that is 25 and 5, then you will get the sum that is equal to 30. Okay, so that's why the answer for this question is nothing but 2. I hope that this is clear to you. Okay, and if you have any doubt, then please do ask. So similarly, see in this case, okay, like the coins, the V value is equal to 11, it means that you want to make the sum equal to 11. The M value is equal to 4, it means that there are total of 4 types of coin available to you. Okay, and you want to make the sum 11. So what we can do, we can just pick a 6 coin, okay, and one coin of 5 value. Okay, so 6 plus 5 is equal to 11. So by just picking 2 coins from this complete, you can get the sum equal to 11. Okay, so that's why the answer for this example 2 is also 2. Okay, so I hope that the question is clear to you, and if not, then please do ask. Otherwise, like, we are going to discuss the solution. Okay, so till now we have discussed that what the problem statement is and what do we require, and we discussed that it is a dynamic programming like problem, standard DP problem, and it's a unbounded knapsack problem. Okay, variant of unbounded knapsack. In unbounded knapsack, what happens, there is no upper limit on how many coins that you want to pick. Okay, you can pick any number of coins that you require. So we can also see another example. Let's say that we have 3 types of coins available. Okay, like 1 2 3, and we want to make the sum 5 equal. Okay, so like there are many possible ways to make the sum 5. Like we can all pick all ones. Okay, we can pick 3 ones and 1 2, then we can pick 2 ones and 1 3. We can pick one coin with value 2, one coin with value 3. It will also give me sum equal to 5. Okay, so if you see in this particular example, you, by just picking 2 coins, you are getting the required sum that is equal to 5. Okay, so that's why, like, this is the minimum value. That's why the answer for this example is nothing but 2. Okay, so how to identify whether this problem could be solved using DP or not? Okay, so let's say that I want to make to identify, like, there should be overlapping subproblems. Okay, to identify whether a particular problem lies in DP or not, the problem should have some overlapping subproblems. Okay, so let's say that you want to make sum equal to 5. Okay, then what we can do, like, let us say that, let us take this example only. Okay, so I have coins like 1 2 3. Okay, so why this problem is a DP problem, let's understand that. Let's say that I picked I wanted to make sum equal to 5. So what I did, I just picked one coin of value 1. Okay, so I picked one coin of value 1. Now the sum required is equal to 5 of 5 minus 1, that is equal to 4. Okay, so now my required sum is equal to 4. So what I can do, I can just call for this sub problem, that is you get the answer for making the sum equal to 4, and you just pick one extra value, one extra coin with this particular answer. Okay, so what it happened here, we break the bigger problem into smaller sub problem. Okay, so it means that this bigger problem could be divided into smaller sub problems. So this is the first part of like where you can apply DP. So the bigger problem could be divided into smaller sub problems. Okay, then the second point is that the smaller sub problems should be overlapping in this case. Okay, so what we can, like, we have choice here. So we wanted to make sum 5, then we called for to make sum 4. Okay, and just we picked 1 from here. Then we can again, like, we again have choice, either we can pick 1, we can pick 2, or we can pick 3. Okay, so if you draw the tree, so like let's say that we picked 1 and then we called for 3. Okay, then we can again pick 1, then we can call for 2, then we can again pick a coin of value 1, we can call for 1. Like in the last we can just pick 1 and we can call for 0. Okay, so from at this point you have another choice that you wanted to make sum equal to 2. So here what we can do, we can just pick a coin with value 2 when we can call for 0. Okay, so it will return you the particular answer. At this point you can call for at this point also you can just pick a coin with value 2. Okay, and then it will reduce to 1. Okay, because 3 minus 2 is like 1. So see here the sub problem started to replicate themselves. Okay, here also we just required to make the sum equal to 1, and we had coins 1, 2 and 3. Okay, here also we wanted to make sum equal to 1, and we wanted we had coins 1, 2 and 3. Okay, let's move forward and see how this subproblem how many more subproblems are there. Okay, that comes in repeated number of times. Okay, so let's move forward. So when we wanted to make sum equal to 1, we had one choice that we will pick just one coin, a coin with value 1, and we will call for 0. Okay, then at this point you also can when we wanted to make sum equal to 3, we can just pick a coin with value 3 and we can call for 0. Okay, what about 4? So at 4 you can just pick a coin with value 2 and you can call for 2 itself. Okay, so see here, this complete subproblem we have already solved. Okay, and we are again calling for sum equal to 2. So here also the problem got repeated itself. Okay, so you can see that here there are a lot of overlapping subproblems. Okay, so that's why in this case we can think of to solve this question using dynamic programming. Okay, so what two properties did we observe? The first property was that we are able to break a bigger problem into smaller subproblem. Okay, and the second property that we observed here is that the subproblem should be overlapping. Okay, it means that we are calculating many times, like in the recursive call we are calculating many times for the smaller subproblems. Okay, so instead of calculating the answer for the smaller subproblem many times, what we can do, we can just store that answer once we have calculated somewhere and we can utilize that. Okay, so that's the main idea of using dynamic programming. So I hope that you got what was the problem and why we can think of applying dynamic programming to this particular question. Okay, and if you have any doubt, if you still have any doubt, then please do ask. Otherwise we are going to discuss the solution for this particular problem. Okay, so let's get back to the question. So the question was just simple, that you are given with some number of some types of coin and you are given with a particular sum. You want to find what is the minimum number of coins that you should pick so that the sum is equal to this particular given value. Okay, and there is one more point to remember here, is that you can pick any coin any number of times you want. Okay, so that's why it is a variant of unbounded knapsack. Now let's back to the like solution. So like you can definitely do what uh, you can make a recursive function. Okay, you can make a recursive function to solve this problem, and then you can do what you can just utilize the memoization. Okay, you can memorize for smaller problems and you can just store their answer, and that then it will reduce the time complexity. Okay, we can do this problem in that manner, and we can also like do what we can like this that we just discussed, like to memorize something. So that's basically top to bottom approach. Okay, and the other thing that we can do here is that we can just move bottom to up. Okay, it means that we will first calculate the answer for smaller sub problems first, and then utilizing those answers we will calculate the answer for bigger problem, and that is the main problem that is given in the question. Okay, so in this particular video we are going to discuss the bottom up solution, that is to build the table from bottom to up. Okay, so what we are going to do here is that, so let's say that we had coins like 1, 2, 3. Okay, so first of all we will have a DP table. Okay, so that is a very standard thing that we do in while solving a dynamic programming question. Okay, so what we are going to do is that, so first of all we will just have one type of coin available. Okay, so we will ignore all these other coins and we will say that we have only one type of coin. Okay, and that value is going to be this one. Okay, then after we have calculated some answer for this, then we are going to add 2 also. Okay, so then we will say that we have two types of coin, like 1 and 2. Then we will calculate answer for this. Okay, then we are going to include the third coin also, so we will calculate answer for using 1, 2, 3. Okay, so similarly we will include one by one all the coins that are available. Okay, and in the last step whatever is the answer that we are going to return. Okay, so for that what we are going, like this point should be clear. Okay, so what we are going to do here is that we are going to include the types of coin one by one. Okay, so initially what we are going to have, we are going to have a DP table, and what this DP table represents, so let's see here. So DP of I represents minimum number of coins. Okay, so it represents minimum number of coins to make change I. Okay, so what does it mean? So DP of 1 will represent what are the minimum number of coins such that I can make change equal to 1. Okay, so let's say that I have types of coin as 1, 2, 3. So DP of 1 is equal to 1. Why? Because we can just pick this one value and my change is equal to 1. Okay, so that's why DP of 1 will be equal to 1. What about DP of 2? So DP of 2 will be also equal to 1, because we can just pick this value. What about DP of 3? It is also going to equal to 1, so because we can just pick 1, 3. Okay, what about DP of 4? So DP of, like, we can have 1 plus 1 plus 1 plus 1. We can have something like 1 plus 3, or we can have something like 2 plus 3. Okay, so in all these cases the sum is equal to 4. But if you see what are the minimum number of coins that we require, so that is nothing but, like, you can have any one of this case. So here we only require two coins, that is 1 and 3, or 2 or 3. Okay, so that's why DP of 4 will be equal to 2. Okay, and what about DP of 5? So DP of 5 is going to be equal to 2. Why? Because we can just pick 2 and 3, and that is going to give me 5. Okay, so I hope that this part is clear to you, what DP of I represents. Okay, so it represents minimum number of coins to make the change that is equal to I. Okay, so let's move forward. So that was the very first line of the code, that is to initialize the, like, understand what the DP array is going to contain. Okay, then let's move forward. So what initially I will fill in this DP table, okay? In this DP table, what should I fill? So here I'm going to fill all the values with a maximum value, okay? And what is this maximum value? This is a very big value. You can take any value, the value should be very big because we want to minimize our answer, okay? So that's why we will pick a very big value and that we will call as max, and we will say that all dp of 1, okay, is equal to max, dp of 2 is equal to max, dp of 3 is equal to max, okay? So we will fill all the values. Dp of the last one should be dp of v, that is equal to max, okay? So I will fill all these values with dp of max. Then I will move forward. See, then the third line is dp of 0 equal to 0. What does this mean? So dp of 0 represents minimum number of coins to make change equal to 0, okay? Because I want to make change equal to 0, so what I can do, I cannot, I will just pick, do not pick any coin, okay? So in that case, how many coins did I pick? So I picked 0 coins, and that's why I was able to make the sum equal to 0, okay? So that's why dp of 0 is equal to 0. So this is this should be clear, the logic should be clear to you. So what, why this line? Because 0 coins are required to make change equal to 0, okay? So that's why dp of 0 is equal to 0. Then I have sorted this complete array, like this coins array. Let's say that I had something like 50, 20 and 10, okay? So what I'm going to do, as I said, I'm just going to include elements one by one. So I will just pick the very smallest element first, then I'm going to pick the next smallest element and add it to my set. So I will pick just 10 and 20, then I will pick the 50 also. So one by one I'm going to pick the smaller elements and add it to my set and calculate answer at each step, okay? So that's why to pick a smaller element first, I have done sorting, okay? So that's why I have done sorting here. Then let's move forward. So this is the point that you need to understand, okay? So how many total number of coins did we had? Okay, so we had total number of m coins. And as I said in this question, what we are going to do. So first of all, we will say that I have only one type of coin, and that is the first coin, okay? Then I'm going to include the second coin, then I'm going to include the third coin. So one by one we are going to include coins into our set, okay? So that's why this loop is running from I equal to 0 till I equal to m, okay? At each step, at each time, what I'm going to do, I'm just going to add one more type of coin, okay? Add one more type of coin to my set, and I will calculate answer for that, okay? Then I will calculate like add one more element, I will calculate answer for that. In the last, when my set is complete, that I have all the elements that were present in the like this coins array, then whatever is my answer, that is going to be my final answer, okay? So let's move forward. So now this loop, understand this loop, okay? So what does this loop means? So this loop, j is going from coins of I, that means the current value of I. Let's say that the current value of I'm going to include the second coin that is having value 2, okay? So I'm going to start from j, from that. Then I'm going to my j is going till the last value, that is the final value that we want to calculate, okay? And at each time I'm calculating dp of j. And what does dp of j represents? dp of j represent minimum number of coins to make change equal to j, okay? And by including the current coin, and what is the current coin? Current coin is equal to coins of I, okay? So I hope that this part is clear, and if you have any doubt, then please do ask. I will repeat once again what I said in this part, okay? So this loop is going to calculate answer for each value that will start from the current value of the current coin, that is coins of I, and it will go till the last value that is equal to the v value, okay? So I will calculate dp of j here, then I will calculate dp of I plus 1, that is equal to j plus 1, okay? And finally I will calculate for dp of v, okay? why I haven't calculated for the values that are less than coins of I, okay, because they will not change, okay, because when I have so let me erase this, then I will explain, okay. So when I have my current value of coins of I is equal to, let's say that 3, okay. So can I include this 3 and make sum less than equal to 3? No. Why? Because like if I want to include this particular coin with value equal to 3, so I cannot make a sum less than equal to 3. Okay. Why? Because all the coins are having positive values, and if I want to include this particular coin into my answer, then I cannot make the sum less than equal to 3. Okay. So that's why we are starting from coins of I. Okay. Now at each point, like this is the uh, main part of this question wherein we calculate dp of j, okay. So what dp of j will be equal to? So dp of j will be equal to minimum of dp of j, because we want to minimize our answer, and dp of j minus coins of I. So what does it means? It means that, let's say that my current value of coins of I, my current coin is having value equal to 4, okay, and I want to make sum equal to j. So let's say that my sum is the j value that I want to calculate answer for is equal to 10, okay. So at this point I want to calculate like make the sum equal to 10, and I have a coin with value 4, okay. So see, I already know about the answer for dp of j minus coins of I, okay. Why? Because we are moving from left to right, and j minus coins of I is going to be lesser than this particular j value, okay. So what is this? 10 minus 4. So I already know the value of dp of 10. So let me show you here, because it must have got hidden, okay. So dp of 10 minus 4 is equal to dp of 6. So I would have already calculated for dp of 6, okay. So that's why I can like do what? That will store the minimum number of coins to make the sum equal to 6, okay. So what I can do, I can have this answer that I have already calculated. Here we are using dynamic programming, and I can just have a value, add one more coin that value is equal to 4, okay. And that's why like 6 plus 4 will give me equal to 10, and like for that one more coin that we are adding, I have added this particular one value, okay. So what my dp of j will be finally, it will be, so dp of j will be equal to minimum of dp of j and dp of j minus coins of I. It means that include the current coin, and calculate the answer, okay. And note one more point here is that, so if this would have been a bounded knapsack problem, okay, so in that case we cannot directly move from left to right, okay, and calculate answer at each step. Why? Because like let's say that we are currently trying to include the ith coin, okay, and that ith coin is coins of I. If I want to include this ith coin, I cannot just look back at my dp of previous values. Why? Because at that point also, if I'm moving from left to right, I would have included this particular coin into while calculating the answer, okay. So in that case what we do, we had to just pick the answer from the previous row, okay. So either in that case you can make a 2D table, okay, or what we can do, we can just move from right to left, okay, because we are moving from right to left. So like we know that we haven't changed the values on the left hand side, okay. So we haven't changed the values on the left hand side, that's why we can calculate the answer at current point, okay. So this is the main difference between bounded knapsack and unbounded knapsack, okay. And finally what we will have in the like whatever we have in the like dp of v value, that is going to be my answer, okay. So in the end what I can do, so in the end I can just return dp of v. So I will first of all check if dp of v is equal to the max value. So if it is equal to the max value, what it means? It means that we cannot make that particular change. Okay. So let's say that the change that we required to make was equal to 3. Okay. And we had coins like 2 and 4. So see here, we cannot make the change equal to 3 by using coins of type 2 and type 4. Okay. So that's why in that case we have to return -1. Okay. And that is given in the question. And if that is not the case, I can just return dp of v. So and v is equal to the change that we require to make. Okay. So the code was very small, okay, but the important point here was to understand the difference between bounded knapsack, unbounded knapsack, okay. Then why we are moving, like why we are able to move from left to right, okay, because this is a unbounded knapsack problem. If it would have been a bounded knapsack problem, then we cannot directly move from left to right, okay. So that these are the main concept that you need to understand, and also you need to understand how this particular flow is answer is getting calculated, okay. And we also discussed like why this is a dynamic programming question, okay. So we saw that like we can divide a particular problem into sub problems, okay, and then those sub problems were overlapping, okay. It means that we are calculating, like in the recursive calls, we are calculating answer for sub problems many number of times, okay. So these were all the like summary that we have done. So I can like show you the final code, so you can take the screenshot of this, and let's try to like run and compile this, and then we will discuss the time complexity and space complexity, and that would be all for today, okay. So for this particular answer, that is the coins with 25, 10, 5 value, we are getting the correct answer. Let's try to submit this. So we are getting the correct answer, and even the the time taken is good enough, okay. Now let's finally discuss the time complexity and space complexity, and till then if you have any doubt, then please do ask, okay. So see here, like we are just doing constant operations here. We are declaring like array, okay. So that's why the space complexity will become order of v actually, okay. And what is v? V is the change that we want to make, okay, because we have declared a dp array. So that's why the space complexity will become order of v. And talking about the time complexity, so here we are like performing sorting, so it will just take order of m log n time, okay, m log m. Then here this loop will run for order of m time. This will loop for order of v time, okay. So it will run of order of v time. So the time complexity will become m log m plus m into v, okay. So this is bigger because like this is mostly bigger, so that's why we'll just take care of that, and the time complexity will become m log m plus m into v, okay. And the space complexity is nothing but order of v, okay. So I hope that this is also clear to you, and if it is not, then please do ask. We have already seen the solution, the bottom up approach, and we have discussed the time complexity, space complexity, and we also discussed how the solution is actually working. Okay guys, if you have any doubt, then please do ask. Otherwise we would end today's session, and also go and try today's problem of the day. So let's see what is that. So today's problem of the day is binary heap operations, okay. So try this out, and if you are able to solve this, then tell me tomorrow, okay. And if not, then we will discuss the solution tomorrow. So I will wait for like a few seconds more, and if you don't have any doubt, then we will end today's session, okay. Okay guys, I see no doubts. Thank you for staying till the end. Okay, and